All right, so now we're going to be talking about matrices. Now, the first thing I'd like to do is go ahead and define what a matrix looks like first. And here's the definition directly from the book. So, an M by N matrix is a rectangular array of numbers with M rows and N columns. So, notice here, each one of these little numbers inside here, these little variables, okay? Um, they represent what we call the elements of the matrix itself. Now, I'm going to zoom in and I'm going to focus right here on this one right here because I think this is pretty legible. Notice that this is the element A12. Now, the one, let me write it off to the right here. A12 in this case means the 1 is going to be the row location, and the 2 represents the column location. So if I asked for the element located in, let's say 3, 2, that would be this element right here, because that would be the third row, second column. All right. Now, normally we will write M by N, and we call this the dimension of the matrix itself. So matrices are a rectangular array of numbers, all right? And we always label the rows first, column second. Every element inside of the matrix will have a lowercase letter in terms of its location, and then it always goes row, column. Now, this is just our very general matrix. And if you can see here across the top in the first row, notice that the first location is always going to be a 1, and it goes like column 1, column 2, column 3, all the way up to column N. Then if we move down the first column, notice that the column number always stays the same, but the row number changes. So you got A11, A21, same column, A31, same column, all the way down to AM1, which is going to be the M row, first column. And then in the lower right hand corner, that just represents, okay, we can allow this to be any size matrix that we want it to be. Okay? So that is exactly what the definition of a matrix is. Now, matrices do not have to look exactly like this. For example, you can have a matrix that looks like this: 2, 3, 1, 4, 5, 6. All right? And this would be a 2 by 3 matrix. You can also have a column matrix, which looks like this: 1, 0, 0. Okay? You can have a row matrix that looks like this: -1 pi 2.3. All right? And we call that a row matrix. So the first one, like I said, is just a regular matrix, 2 by 3. The middle matrix is going to be a 3 by 1. That's a column matrix. Or sometimes you will hear it referred to as a column vector. And then this is going to be a 1 by 3, which is a row vector or a row matrix. Now, the next thing that I want to kind of go over, all right, would be a special type of matrix. So we have what we call an augmented matrix. So an augmented matrix is a matrix that is a representation of a linear system. Okay? So, for example, we may have the linear system 3x plus 2y minus 4z equals 1. X plus 3z equals 1/3. And then x minus 2y plus z equals -3. Okay? Now, this is our linear system, and we could convert this into an augmented matrix just by writing out all the coefficients and what they equal. So, like for example, the first row is going to be 3, 2, -4, 1. The second row is going to be 1, 0, 3, 1/3. And then finally, the third row will be 1, -2, 1, -3. Now, sometimes, and it all depends on the book that you have and the professor that you have. Sometimes you will see either a dash line or like a solid line right here. And that definitely screams, okay, this is an augmented matrix. The left-hand side will be the coefficients of the variables. And then the right-hand side are going to be nothing more than the constants that they're equal to. All right. If you don't see anything written here, okay, then make sure you read the question carefully because it will say this is an augmented matrix or this matrix came from a linear system or something like that, okay? But I don't know, I'm pretty good at drawing the line there, so I'll always just remember to keep the line there so you know, okay, we're dealing with an augmented matrix. Now, one thing that we should be, I hope, comfortable with is converting back and forth. So earlier you watched, I converted this linear system into a matrix. So you should be comfortable with taking an augmented matrix. Let's say it's 0, 1, 3, 4, 1, 1, 1, -1, and 0, 0, 3, 7. And you should be able to convert this back to a linear system. So each column is going to represent one of the variables that we have. So this is just going to be 0x plus y plus 3z equals 4. X plus y plus z equals -1. And then 0x plus 0y plus 3z equals 7. And if you wanted to, and this is what honestly I would do, is wherever you see the zeros, I won't even write them. I would just clean this up just so it says y plus 3z equals 4. X plus y plus z equals -1. And then finally 3z equals 7. So we should be able to go back and forth between an augmented matrix and then its linear system equivalent. So now the big question should be, okay, we know how to write a matrix, we know how to identify matrices, and we know how to find their dimensions. The question now is, well, what can you do with them? So the first thing that we're going to study with matrices is nothing more than just elementary row operations. Now, we've already been doing this. We just did it with the systems of linear equations using certain techniques. So I'm going to just go ahead and just take this from our book. Here's what we're allowed to do with matrices. And like I said, we call these elementary row operations. So one of the things that we can do is we can add a multiple of one row to another. The second thing we can do is multiply a row by a non-zero constant. And then the third thing we can do is interchange any two rows that we want. Now, if I go back into our notes back here into systems of linear equations, notice here, we basically have three rules that we need to know when we're solving systems. You can add any two rows to the equations together to form a new equation. That's the same exact thing as saying add a multiple of one row to another. You can multiply an equation by a non-zero constant. That's the same as saying multiplying a row by a non-zero constant. And then we can interchange any equations that we want, as long as we simplify them correctly. So notice those are the same exact things here, and they should be. Because remember, all a matrix is a simplified version of a linear system. It's just written in a rectangular array of numbers. All right? Now, the notation that we use is a little bit different. So if you recall, let me go back to our previous notes here. If you recall, let me find a really good example where I did all that. So here we go. So if you recall in this example right here, sorry. There we go. This is what I wanted. I would write a circle equation 1 plus -1 equation 2. All right? And the reason why I wrote that is I wanted you to be sure that you knew exactly what equation did I use and then what non-zero constant I used to actually multiply that row by. with matrices, we do the same exact thing. It's just instead of writing, EQ for an equation, what we do is we're going to write R for row. So, for example, what this is telling me here is Ri plus K Rj replace Ri. So all this is saying here is I'm going to take row and whatever row I want it to be. So if I want to be specific here, I could say, well, I want to take row 1, I'm going to multiply it, or I'm going to add it to 2 times row 2, and then we're going to replace row 2. So the notation here is just, instead of using EQ, we're just going to use R. So if you want to add a multiple of one row to another row, this is the notation you would use. If you want to multiply any row just by a non-zero constant, that looks like this. So you would have a constant times Ri. So an example of something like that would look like -3 times row 2. And what I would do is I would say replace row 2. So you're going to take -3, multiply it by row 2, and then replace row 2. And I'm really good at writing out what I did. And then finally, interchanging any two rows, that would look something like this, where you have a double-headed arrow. So you can say like you want to interchange row 1 with row 3, and that's what it would look like there. All right, now your book has a really good picture of what is actually happening here, and it compares the same problem done in 2 different ways. So I'm going to copy and paste that into our notes. Okay, so I'm back. I copy and pasted this into our notes, and this is the same exact problem, just done in both ways with the proper notation. So first, let's look at the system. We have x minus y plus 3z equals 4. We have x plus 2y minus 2z equals 10, and then 3x minus y plus 5z equals 14. And if you notice, that's exactly what the augmented matrix would look like. Now, like I said, I would write this little line, and like I said, it all depends on the book publisher. If they want to put that line, if they have the technology to do that, they will. If not, they leave it like without a line. But they'll tell you it's an augmented matrix. All right. So now let's look at our first step here. In this very first step, it says, okay, we're going to add -1 times equation 1 to equation 2. Now, I would write that like this: -1 times equation 1 plus equation 2. All right? And I'd put a circle around that. The matrix notation of that would just be R2 minus R1 replace R2. So let me go ahead and highlight it as I read it so you can see it. All right, because I don't think I did a good job there. So now, here we go. So R2 minus R1 replace R2. And I'm going to zoom in here because I do have a little bit of a gripe with this. All right. I completely understand what they're doing here. But to be honest with you, I would probably have written this as R2 plus -1 times R1 replace R2. That's what I would have done. All right. Because I just like keeping the plus sign in between because I know I'm going to be adding these rows together. All right. Now, let's look at the next step. The next step would be they're going to add -3 times equation 1 to equation 3. So that's going to look like this: -3 equation 1 plus equation 3. Now, how do you write this in matrix form? Once again, it's going to be R3 minus 3R1 replace R3. Okay? And every time you make a matrix move, that's what you're going to do. All right? The key here is to understand what you're multiplying by and what you're adding together. All right? Now, earlier I mentioned that there's a very systematic way on how to do this. All right? So what we're going to do is we're going to take our elementary row operations and we're going to combine them with this brand new form that we're going to be interested in. So let me go ahead and copy that into our notes. All right, so we have two different forms that we're going to be very interested in. The first form is called row echelon form, and the second is called reduced row echelon form of a matrix. They are both extremely similar, okay? Just one of them requires you to do a little bit more work. So, whenever you're reducing a matrix, you're always going to get it into row echelon form first, okay? And then based off that, if you want to, you can take this even further to get reduced row echelon form, okay? And it all depends on how large the system is, how comfortable we are with doing this. To be honest with you, once you get the approach on how to do this, I think you're going to end up finding that the more you do this, you're going to be going all the way down into reduced row echelon form. Okay. Now I went ahead and I did something earlier today because I really wanted us to be able to use this tool to our advantage. So I went ahead and because I got a brand new laptop a couple weeks ago and I haven't done this yet, but I went ahead and downloaded a new version of this calculator so I can show you how to use this calculator. So, one of the things you're going to notice in the very first column in light blue, okay, it says the word matrix. So, we're going to go ahead and hit second matrix. And you got all these different names for matrices. So, names for matrices are always capitalized. Then you have this math menu, okay? In fact, let me can I do a is that what I want? Yeah, there we go. That's what I want. So we get a, I can, maximize this so you can see a little bit more. So you got the names. Then if you hit the arrow over button, you have math. Now these are all the different math functions that you could do with matrices. So you can find the determinant, transpose dimensions, fill, identity matrix, a random matrix. Number 7 would be an augmented matrix. And if you keep just scrolling down, you're going to end up seeing two versions, which is letter A, REF, and REF stands for row echelon form, and then RREF, which is reduced row echelon form. So I'm going to show you how to do these by hand, and I'm also going to show you how to do this by a calculator because, you know, eventually some of us may be going on for higher level mathematics, and you got to know how to do this because you're going to be looking at potential systems where instead of having 2 or 3 or possibly 4 variables, you're going to have 20, 40, 50. You can even have n amount of variables. All right. When I was in grad school, we did a problem where we were testing out the just how fast can our computers compute an n-dimensional matrix. And I no joke, at the time I had a very powerful computer, which, like I said, at the time, and it took my computer like 2.5 days of just running before it actually solved the answer. So these can get crazy real fast, but we're gonna keep it nice and simple. So let's go ahead and let's talk about and let's discuss the differences between row echelon form and reduced row echelon form. So a matrix in row echelon form will have these characteristics, all right? And it has to satisfy these three conditions. Number 1, the first non-zero number in each row, reading it from left to right, is a 1, okay? This is called the leading entry. Number 2, the leading entry in each row is to the right of the leading entry in the row immediately above it. So what that means, all right, is if I have this matrix, and I'm just going to go ahead and draw an augmented matrix that looks like this. So this number 1 is our leading entry, which means in the next row, the next leading entry has to be right there. So I'm going to highlight that position. Has to be this position right here. So it has to be one column over, one row down. And that means that the next, and I'm just going to make up some numbers here, 3 and 4. So for the next entry, it has to be a 1, and it has to be one row over, one row down. And this could be something like -3. All right, and I'll highlight this as well. Okay, so these are going to be all of our entries right there. So number 1, the first non-zero number in each row has to be a 1. We have that. Number 2, the leading entry in each row is to the right of the leading entry in the row immediately above it. And then number 3, all rows consisting entirely of zeros are always at the bottom of the matrix. So what that means is this. So let me erase this. You could run into a situation where you have a matrix that looks something like this. Actually, here, let's do this. And notice that row 2 has a row of all zeros. So what I would do is I would say, okay, well, I'm going to swap row 2 with row 3. So I would write this as 1, 2, 3, augmented -5, 0, 1, 5, 6, and then all my zeros right there. So you have to do that, okay? So as long as you meet these first 3 conditions, we call that row echelon form. Now, if you want to take this one step further and make it reduced row echelon form, then what you're going to have to do is every number above and below each leading entry is a 0. So if I were looking at this right here, and like I said, I'm just going to make these numbers up. All right, I'll put pi there because that's a number. All right. Notice here you have ones down this main diagonal that actually has a name. It's called the main diagonal. And every number above or below each leading entry in every row is a 0. That is called reduced row echelon form. Okay? Now, if you were kind of catching on to what I was writing earlier, if I were to write this matrix right here, we'll call it matrix A. If I were to rewrite this in system or linear system form, notice I would get 1x equals 5, 1y equals 3, and 1z equals pi. And to be honest with you, you don't even need those ones out front. So this would just be x equals 5, y equals 3, and z equals pi. So that's what reduced row echelon form gives us. It gives us the actual value for each unknown quantity or unknown variable that we have in our system. If we had something in just row echelon form, and that's going to look like this. So 1, 2, 3, 5, 0, 1, -2, 3, and then 0, 0, 1, 7. Then in linear system form, this would look like x plus 2y plus 3z equals 5, y minus 2z equals 3, and then z equals 7. And what you would have to do here is you would have to backward substitute to find all of the missing variables. So, in essence, row echelon form will give you a really nice starting point to actually find each one of the missing variables. Reduced row echelon form doesn't require you to go back into the linear equation form. You could just keep going with your technique, which I'm going to show you here in a second. You can keep going with your technique to just find all the answers to the system. So I guess the big question here is, okay, well, how do you do this? So one of the methods that we use has a name, and it's called Gauss elimination. And I keep saying this, and hopefully it's starting to make a little bit of sense, but this is very, very systematic. All right. So I just kind of took this from your book because your book does a really good job at explaining this, and it's no use me writing everything that I'm just going to be reading off the page anyways. So there is a systematic way to put a matrix into row echelon form. Here's how we do this. Start by obtaining a 1 in the upper left-hand corner, and then you're going to write zeros underneath it. So here's what's happening here, okay? Let's say we just have a regular matrix. All right, and we're going to augment this. No matter what this first element happens to be, A11, you are going to have to make this a number 1, okay? Then you're going to take and make zeros underneath it, All right. And I'm going to show you how to do this. But this is the process on how we do this. So you create a 1 in the upper left-hand corner, and then you go zeros underneath. Then you go one row over and one column, or I'm sorry, one column over, one row down, and you make this leading entry a 1. And then you're going to make everything underneath that a 0. Okay? And then finally, you go over one column and down one row, and you make that leading entry a 1. Okay? Now, up above here, these are going to be different values. They're going to be numbers. They could be 0 or they could be anything, any real number out there. But regardless, this is called row echelon form. Okay? So, like I said, if you read these directions against upper left-hand corner, create a 1, zeros underneath. Then you obtain the next leading 1 in the next row, zeros underneath. Then you go one more row over, and you make everything underneath that zeros. All right? And you just keep doing that process until you have this nice main diagonal right here of all 1s with a lower triangular matrix of all zeros. All right? Now, how do we make something in row reduced echelon form? Okay? Well, it's actually very simple. So you start off the same way. So we're going to do our 1 with zeros underneath, a leading term with the 0 underneath. Then we have a 1 right there. Okay? However, you don't stop here. You are now going to go, once you create this leading entry in the very last row, very last column of your augmented matrix, you make zeros above it. Then you come back and you will go back this way and up here and make that a 0. So if you think about this, and I'm going to use a different color here, for row reduced echelon form, you start up here in the upper left-hand corner, you make it a 1, then you make all these zeros. Then you start in the middle, you make that a leading entry a 1, and you make all those zeros underneath. Then you're going to make this a 1 and make all of these zeros above. And then finally, you come back to that 1 in the middle and you make that a 0. So sometimes it's really easy just to think about this in terms of like a little circle. Like you're just going to do it like that right there. So I guess it's not a circle, more like a square. Okay? And like I said, I'm going to show you how to do this. It's not difficult at all. All right, so here's our first example. Now, if you want, what I would do if I were you, honestly, is maybe get a snack, get something nice to drink, and just follow along. Personally, I would watch it first, then I would rewind, and then walk through it together with the video. So here's our first system that we're going to be looking at. We got x plus y plus z equals 2. We get 2x minus 3y plus 2z equals 4. And then finally, 4x plus y minus 3z equals 1. All right, so here's our first system, and the directions are going to be really simple. Solve, or how about this? I'll be even more specific. Right into row echelon form and solve. Then reduced row echelon form. Okay? So the first thing we're going to have to do here is create our matrix. So it's going to be 1, 1, 1, augmented with 2. Then 2, negative 3, 2, 4. And finally, 4, 1, negative 3, 1. Okay? Before you do any moves, make sure you go back into the linear system and check to make sure you copied every single coefficient down correctly. The worst possible thing you can do is copy something wrong at the very start spend 20 minutes doing a problem and then only realizing that you copied down the problem incorrectly. So take the time and just check it to make sure everything is correct. All right, so I definitely paused the video just so I can check to make sure everything's correct. Now, step one, we need to make this upper left-hand corner a +1, and it's already a +1, so we don't have to worry about that. However, what we're going to have to do is we got to make that entry a 0 and this entry a 0. So what I'm going to do is this. First thing I'm going to do is write an arrow, and that's going to show that I'm making a move, and I'm going to take -2 times row 1. I'm going to add it to row 2, and then I'm going to replace row 2. So if you notice, I am not replacing row 1 at all. So I'm going to leave row 1 the same. So 1, 1, 1, 2. And what we're going to do is we're going to go ahead and make our multiplication. I'm going to write out these multiplications so you can see it. So we got -2 times 1 plus 2, and that's going to equal 0. So that's going to go right here. And I just move from left to right, okay? So the next entry is going to be, and I'll highlight it here for you so you know exactly where I'm looking. I'm looking right there, okay? So this is going to be -2 times 1 plus -3, and that's going to equal -5. So -5 goes right there, all right? And then finally, I move over here. Well, not finally, I need to do more, but you'll see. I'm going to take -2 times 1 and add 2. So -2 plus 2 is 0, so I put a 0 right here. And now, finally, this is going to be the last one. Give me a second. Come on. Come on, work with me, pen. Right there. So I'm going to take -2 times 2 and add 4 to it. So -2 times 2 obviously is -4, and -4 plus 4 is 0. So I put a 0 right there. And we have just did our very first row operation, okay? Now, since row 2 is done, I'm going to have to mess with row 3 now. All right, so let me erase this. Actually, I'm just going to pause the video and erase what I don't need. All right, I'm back. I just cleaned it up. So now what we're going to have to do is we're going to have to make the third entry in column 1 a 0 as well. And to do that, we're going to take -4 and multiply it by row 1, add it to row 3, and then replace row 3. So I'm going to do this the same exact way. I'm just going to write out what I'm doing so you can see it. And then as I progress, I'm not going to be doing that as much. So -4 times 1 plus 4 equals 0. So 0 goes right there. All right. Now I move from left to right. So it's going to be -4 times 1 plus 1. So -4 plus 1 is -3. That goes right there. All right. I'm looking at this one now. So it's going to be -4 times 1 plus -3. That's going to be -7. Okay. And then finally, I'm looking here in my augmented part. It's going to be -4 times 2 plus 1. So -4 times 2 is -8, and -8 plus 1 is -7. All right. So congrats. You've done your first column with doing an with doing row echelon form. Okay? So luckily for us, well, for me specifically, I am just going to copy and paste. Oh, I didn't want to do that. I wonder why it's doing that. I don't like that. Oh, I think I know why. There we go. I'm just going to copy this, and I'm just going to paste it directly underneath here. And what we're going to have to do now, according to the directions, we go over one column and down one row. This has to turn into a number 1 now, and it has to be a +1. So how do we go about doing that? Well, we're going to take negative 1/5, multiply times row 2, and replace row 2. So I'm going to go from left to right. Notice I'm not replacing any other rows, so they all stay the same. I'm just going to take negative 1/5 and multiply it times 0. So that gives me 0. I'm going to take negative 1/5 and multiply it by negative 5. So that's going to be positive 1. I'm going to take negative 1/5 and multiply it by 0 to give me 0. And then negative 1/5 times 0 again to give me 0. So if you notice, we're starting to get that row echelon form that we want. It's slowly coming. All right. I'm going to copy and paste this again. Just move it down. There we go. So let me get out my highlighter one more time. Notice we have a 1, upper left-hand column, all zeros underneath. Go over one row, down one column. Excuse me. We got a 1 there, but now we need to make this negative 3 a 0. So just like in the very first step, we're going to use that middle row in the second column, and we're going to use that to get rid of the 3, or the negative 3. So I'm going to take 3, multiply it times row 2, add it to row 3, and replace row 3. Okay? So I rewrite everything else exactly how it looks. Oops, sorry. That's supposed to be a 2. 0, 1, 0, 0. Except I'm going to take I'm going to take 3, multiply it times each element in row 2, add it to each element in row 3, and replace row 3. So 3 times 0 plus 0 is 0. 3 times 1 plus negative 3 is 0. And then finally, 3 times 0 plus negative 7 is negative 7. And 3 times 0 plus negative 7 is negative 7 again. All right. So now if you look at it, it's really starting to look pretty good. It really is, not going to lie. All right. Erase my work. I'm going to go ahead and copy this and paste it again. So get out my highlighter again. I'll use green. Notice in our leading entry, we have a 1. In the second row, we have a 1. In both situations, we have zeros all underneath. So the last thing we need to do is make this negative 7 a positive 1. And to do that, we're going to take negative 1/7, multiply it times row 3, and replace row 3. My other rows all stay the same. Negative 1/7 times 0 is 0. Negative 1/7 times 0 is 0. A negative times a negative is a positive, and 1/7 times 7 is 1. And then negative 1/7 times negative 7 is the same exact thing. It's going to be 1 again. So finally, we have what we call row echelon form. All right. We definitely got it right there. So what you can do from here is you can stop. You can stop with the elementary row operations if you wanted to. All right. And you can take this matrix and convert it back into a linear system of x plus y plus z equals 2, y equals 0, and z equals 1. So notice you already know what z and what y equal just by rewriting this into back into a linear system. Which means if we know what if we know what y is and we know what z is, we can use backward substitution for both cases and say x plus 0 plus 1 equals 2, which means we have x plus 1 equals 2. Subtract 1 from both sides. We get x equals 1. So the point at which all these three lines, or I'm sorry, all these three planes will cross is going to be 1, 0, 1. And that is how we solve using Gauss elimination, and more specifically, stopping at row echelon form. Okay? Now, let's say you just didn't want to stop here. I'm going to show you how to continue for row reduced or reduced row echelon form. All right? So hopefully I still have it saved here. So if you want to continue, you just keep continuing. So let's see, I'm just going to make these our ones because that's what it is. And what I'm going to have to do now is this. Notice I have, and to be honest with you, each one of these numbers right here in this main diagonal, another name for them are pivots. And it's just like a pivot foot in basketball. In basketball, when you stop dribbling, you one leg is supposed to be stationary, the other one can move. So we use those pivots to create zeros around our matrix. All right? So, excuse me. So what we're going to do here is we're going to remember that flow. We start in the upper left-hand corner. We come down to the right, up, and backwards. All right? So we're just going to continue doing this by making zeros everywhere that we can. All right? So let me clean this up here so there's not all these shapes and everything. All right, so that's supposed to be a 0, 1, 1, 1. Beautiful. I love the way this looks. All right, so we're going to continue by making everything above that leading entry a 1. I'm sorry, a 0. Sorry, a 0. Now notice we already have a 0 directly above. So this element right there, we're going to have to make that a 0, and that's going to be easy enough. We use our pivot. So -1 times row 3 plus row 1, replace row 1. All right, so I'm going to keep row 3 the exact same. 0, 0, 1, 1. And I'm going to keep row 2 the same because I'm not replacing that either. All right. And I'm just going to go from left to right, and I'll write them out for you just so you can see. And what I'll do here is I'll draw the arrow where they're going to go. All right, just let me get rid of this real quick. All right, so here is going to be our first thing that we're going to mathematically manipulate. So -1 times 0 plus 1 equals 1. So there's going to be a 1 there. Now, right here, -1 times 0 plus 1 equals 1. So there's a 1 right here. All right. Now we move over to right here. -1 times 1 plus 1. Well, that is definitely a 0. So this becomes a 0. And then finally, the very last column right here. -1 times 1 plus 2. Well, -1 plus 2 is going to be +1. So we put a 1 right there. All right. Now, the last thing we need to do. Sorry, I'm just going to erase real quick. Is I need to make this right here a 0. Okay. So to do that, I'm just going to copy and paste this and do it directly underneath. Oh, doing that thing again. There we go. So copy and paste. There we go. And if you notice, this 1 is in that second column. Therefore, I'm going to use row 2 as my pivot. So I'm going to do -1 times row 2, add it to row 1, and replace row 1. Row 2 is going to stay the same. Row 3 is going to stay the same. It's the row 1 that could potentially change. So once again, I'm just going to draw the arrow so you know where I'm going. So I'm in this first column. So it's going to be -1 times 0 plus 1, which is 1. Then, equals 1. Now, let's move over to the right. This is our pivot now. -1 times 1 plus 1. Well, that's going to be a 0. I put a 0 right there. Move over one column. This is going to be -1 times 0 plus 0 equals 0. Oh, all right. And finally, in our last column, we're going to do -1 times 0 plus 1, which equals +1 again. And notice here, this is row reduced echelon form. And what makes it row reduced is you have ones down the main diagonal and zeros everywhere around it on the left-hand side of the augmented matrix. And as you can see here, we still get x equals 1, y equals 0, and z equals 3. Okay? So that is how you do this. Practice makes perfect, obviously. What I'm going to do now is I'm going to transition. I want to show you how to do this on a calculator just so you can see how it works. All right, so I got my calculator, and all calculators, all scientific calculators will have some sort of matrix function. However, if you do not have a TI-84 or something like that, uh, you're going to have to find your model and then try to YouTube it. If you can't find something, just let me know and I'll try to find something for you. But there's a lot of resources out there that exist for us. So I'm just going to show you how to use your calculator here to do this. We're going to do the same exact problem. First, we're going to do row echelon form. Then we're going to go ahead and do reduced row echelon form. And what you're going to notice is it actually takes you more time to type all this stuff in than it does for the calculator to do it. So how do we do this is in the far left column, you're going to see the matrix button, which is right above the inverse button. So second matrix. Then you're going to scroll all the way over to edit. And we're just going to go ahead and store this in matrix A. All right, so we'll go ahead and hit enter. Now it's going to ask for the dimensions of the augmented matrix. So we're going to have a 3-row, 4-column. Okay? Now, if you look in the lower left-hand corner, I wonder if I can make this any larger. There we go. That looks pretty good, I guess. Hopefully it looks good on your screen. So now we're going to type in all the coefficients and then the augmented part. And as soon as you type in a number and hit enter, it goes from left to right, and then it'll just go from left to right until it's done. Then it moves on to the next row and so forth. So if you look at the original problem that we had, all right, it is going to be 1 enter, 1 enter, 1 enter, and then 2. Okay? Now, the next row is going to be 2, -3, 2, and 4. Okay? And then finally, we're going to have 4, 1, -3, and 1. Now, after you type the very last element and you hit enter, you're done. You don't have to do anything else in terms of entering information. So we're going to go back to the matrix screen. All right. And we're going to scroll over here to the right where it says math. All right. Notice in matrix 1 or matrix A, it is a 3x4. So we can come over here to the math menu and we're going to scroll all the way down until we see REF. Now remember, that is row echelon form. So I'm going to hit enter here. Oh, geez, I did the bad mistake. I knew that would happen. All right, so after you're done with this, hit second quit. The newer calculators don't do that anymore, but this one is, let's be honest, it's I didn't pay for this, so don't turn me in. But once you get back to the home screen, then you go back to the matrix, go over to math, scroll all the way down until you see REF, and that's what we want right there. And this is going to give you the row echelon form of any matrix you want it to be. So we go back to the matrix menu, underneath names, and just hit enter for matrix A. Close the parenthesis and hit enter. And there it is right there. All right. Now, your echelon form may look a little bit different from what we had. The reason for this is when you go to program something, and this is definitely beyond the scope of the class, but you want to do it in such a way that it minimizes the cost of the actual CPU and the RAM inside your computer. What that means cost is the fact that you want to try to do this with the least amount of operations so that your computer runs more efficiently. That's it. All right. So here's what your TI-84 will give you in terms of row echelon form, and it's 100% correct. You can even take this backward substitute, and you're going to get the same exact answers that we did previously. To do row reduced echelon form, which I'm going to be honest with you, that's the one you should be doing. You would go back to that matrix menu again, go over to math, scroll all the way down until you get to RREF, which is reduced row echelon form. Select the matrix that you want that to happen to, and just go ahead and hit enter. And notice we get that main diagonal, and then the augmented part. You can see my mouse moving up and down. That's where that line would be. X equals 1, Y equals 0, Z equals 1. Okay? That's how you use a calculator to do all of this very quickly, very efficiently. Okay? Now, there are definitely tons of websites that can help you, but the problem with the websites, all right, and notice all I did was just typed in RREF calculator, but the problem with websites are some of them are not user friendly. Some of them are great, not gonna lie, some of them are absolutely fantastic, all right? But others, it's like, oh. So here's one right here, all right? And already I see something I don't like, which is whatever this notation is in the middle. All right. But whatever. You can change the size of your matrix. This will be a 3 by 4. Then you're going to have to type in all of your coefficients. So 1, 1, 1, 2. And then it's going to be 2, -3, 2, and 4. Then we have 4, 1, -3, 1. Do you want this reduced? Leave it check mark, yeah, and then go ahead and calculate. And it will actually give you a nice systematic approach on how you do this. But at the end of the day, if you scroll all the way down, the reduced row echelon form is 1001, 010, and 0011, which means x equals 1, y equals 0, and z equals 1. Now, all of these are nice, okay? The fact of the matter here is this. If you want to use some sort of online tool or your calculator, that's great. But what's going to happen later on when you don't have that functionality? Or maybe you will and you never have to worry about it again. That's fine too. All right. All I want you to do is just be honest with yourself. All right. Know how to do it by hand first. That way you can appreciate all the steps here. Okay. So let's see here. The next example, I need to do at least one example of each where you come up with an inconsistent system and then an infinite solution system. All right. So here's an example where we're going to come up with an inconsistent solution. I want to show you when that occurs. All right. Now, this video is already an hour long, so I'm going to speed up my process here a little bit. Okay. So, upper left hand corner, we want that to be a 1. It already is. That's fantastic. Underneath here, we need to make the 2 and the 1 both zeros. So, what I'm going to do is I'll do row 2 first. So, to do that, I'm going to take -2 times row 1, add it to row 2, and replace row 2. Row 1 is not going to change. Okay. So row 2 is going to turn out to be 0, 1, 1, -10. All right. Now, we need to do row 3. So to do that, I'm going to take -1 multiplied by row 1, add it to row, oh, sorry, give me a sec, let me fix that. Add it to row 3 and replace row 3. So after I do that, I'm going to get 0, 1, 1, 8. Okay? Now, please go through the math and check yourself. Now I'm just going to copy and paste. Notice in my next leading entry, it's already a 1, and that's great. So I need to make that element right there a 0. So to do that, I'm going to take -1 times row 2, add it to row 3, and then replace row 3. So row 1 is going to stay the same. Row 2 is going to stay the same. Row 3 is actually going to change. So after you do that, you're going to get 0, 0, 0, 18. Okay? Now, here we stop. And there's a reason for that. So first, let me get out my red marker that says stop, so you know that. And I want you to look at this very last row. All right? There is a major problem with this last row. Remember, if I were to go ahead and convert this matrix here back into a linear system, here's what it would look like. X minus 3y plus 2z equals 12. That's okay. Your second row is going to be y plus z equals negative 10. And that's okay. The last row says 0 equals 18. And you and I both know 0 does not equal 18 at all. They are not the same number. Therefore, we stop and write the word inconsistent. And that's it. That's it. In fact, your calculator will actually go through this and it'll show you. Let me just demonstrate real quick, okay? So let's get out our calculator again. Turn it back on. Let's clear that out. We're going to go back to the Matrix. Matrix is a good movie too, by the way. Really like. I didn't like the second or the third one or the last one as much, but boy, that first one was pretty good. Maybe because it's the first time we ever saw it. Anyways, let's go ahead. Let's type in the elements. So we got 1, negative 3, 2, and 12. All right. Then we get 2, negative 5, 5, 14. And then finally 1, negative 2, 3, and 20. Now remember, don't make the mistake I did last time. We're going to second quit. We're going to go back to the matrix. And it doesn't matter which one you do. You can do REF or RREF. We'll do REF. And we're going to row echelon form matrix A. And when I hit enter, look at that very last row. You have 0, 0, 0, 1. So right there, you know, boom, you got to stop. Because you cannot have, and I'm going to write this down, and this big screen is going to go away as soon as I write this down. In fact, let's do it in red because it's so important. We cannot have a row of zeros in an augmented matrix equal to a non-zero constant. All right? That is very, 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 very bad. All right? So you cannot have this final row of zeros and have a non-zero constant on the right-hand side. That's how you know, boom, stop, inconsistent system. Okay? So now that I showed you one where it's inconsistent, I want to show you one where it is consistent, but it's dependent, meaning there are infinite amount of solutions. Okay, so here's the final example. And this is an example where we're going to have infinitely many solutions. So we're going to see how that or what that looks like. And then we're also going to write out the solution in its proper form. So remember, you want this upper number right here to be a positive 1. Now, if you wanted to, you could multiply negative 1/3 times row 1 and replace row 1. But I'm not going to do that. Because by doing that, you actually get fractions, and I want to avoid that. All you got to do is just take a second, look at your entire system and go, well, what if I just did this? What if I took row 1 and swapped it with row 3? Because you're allowed to interchange any two rows you want. And by doing that, you get 1, 1, negative 10, negative 4. -1,075. Row 2 stayed the same. And now row 3 is -3, -5, 36, and 10. And now if you look, without doing any math, I got a 1 in the upper left-hand column. And that's exactly what I wanted. So now I'm just going to copy and paste this. I don't know why I put it over there. That was weird. Put you back over here. There we go. Now we know we need to make that entry a 0 and this entry a 0. So we're going to go ahead and do that. And we're going to just take our time with it. So let's see. The first thing I'm going to do is I'll do the row 2. So I'm going to take row 1. I'm going to add it to row 2 and replace row 2. Row 1 stays the same. Okay. So now, after you take row 1 and you add it to row 2, you're going to get 0. Oops, sorry. 0. 1 plus 0 is 1. -10 plus 7 is 3. And then -4 plus 5 is going to be +1. So you get 0, 1. Oh, sorry, -3 and 1. That's bad mistake right there. Like that would have ruined my night. All right, so I'm so glad I caught that. Now, we're going to take 3 times row 1, add it to row 2. I'm sorry. Add it to row 3 and replace row 3. So if you do that, you're going to get 0, -2, 6, -2. Okay? So everything so far is looking awesome. Let's just copy and paste this. Now what's beautiful is right here in our next leading term, we already have a 1, so we don't have to worry about multiplying by a constant. But we are... Why isn't that racing? Don't care. We are going to have to make this a 0 underneath. So to do that, we're going to take 2 times row 2, add it to row 3, and replace row 3. Row 1 stays the same. Row 2 stays the same. Now row 3, after you do that, is going to be 0, 0, 0, 0. Okay? Now, if you stop right here, which you're totally allowed to do, you can stop right here. All right? I want you to look at this very last row. Now, this is an entirely different situation than above. Because remember, and I'm going to scroll up a little bit. You cannot have a row of zeros in an augmented matrix equal to a non-zero constant. If we go to our row, notice we have all zeros. And that is 100% legit. In fact, if I were to write out this system, this would be x plus y minus 10z equals -4, and that's good. Y minus 3z equals 1, and that's good. And then this final row obviously would be 0 equals 0, which is true. And as soon as you see that, you should be thinking infinitely many solutions. So if you remember from the previous video, how do we write this? Well, we're going to erase this and just write z equals t, and we're going to solve each one of these rows above. So we'll solve this for y and solve this row for x. Because remember, we want a solution point where this is going to be x, comma y, comma z. All right. So let's go ahead. Let's do that. I'm just going to erase this real quick. We know z equals t, so I'm going to come and do this backward substitution. Y minus 3 times t equals 1. And if I solve this for the variable y, I get y equals 1 plus 3t. Put a little box around that. Now, I backward substitute again. I get x plus, instead of writing y, I'm going to write the quantity of 1 plus 3t. And instead of writing z, I'm going to write minus 10t, and that equals -4. So now I'm just going to go ahead and group any like terms that I can. So I get x plus 1 minus 7t equals -4. Now I'm going to move the 1 by subtracting it from both sides. X minus 7t equals -5. And then add 7t to both sides to give me x equals -5 plus 7t. For our final answer of -5 plus 7t, comma, 1 plus 3t, comma, t. And that is going to be our final answer right there. Okay? So that's how this stuff works. Gotta be honest with you, you're really, really, really gonna like a calculator when you do this, because it definitely saves so much time. Now, I do have one more example, except I'm gonna just use a calculator for this entire example, because if I didn't, we would be here for another 30 minutes. All right. So here's what I want to look at. We're going to look at this system right here, and it is an augmented system. So it's going to be 1, 2, -3, -4, 10, 1, 3, -3, -4, 15. And then we're going to have 2, 2, -6, -8, 10. So, yes, we have in this situation more columns than rows. And you can totally have that. All right. So what we're going to do here, like I said, is we're just going to go ahead and type this into our calculator. And I'll pause the video, type it into the calculator on the side, and then we'll go ahead and we'll see what this looks like in a reduced row echelon form. Okay. Okay, I'm back, and I went ahead and typed everything in. So our dimensions are going to be a 3 by 5 matrix. And if you look here, I just went ahead and I just typed everything in. All right. So I'm going to go ahead and quit. Then I'm going to go back to our matrix screen, go down to math, and I'll go down to row reduced echelon form, which you can use either, but I'm going to use this one. And I'm going to go ahead and say, okay, let's do that for matrix A. And I want you to see what happens here. All right, so here's going to be our matrix. All right. And I'm going to go ahead and just copy this down for us. All right. So just give me a second here. I'm going to pause the video and just copy it down. All right, so I'm back. So the notation I used was RREF, which tells me I used my calculator. And here's what the resulting matrix was. And we got to be really careful when we write this out. So I think it always helps if we write out what this system is going to look like first. So I'm going to go from left to right. This is going to be my X column, my Y, my Z, and I'm going to call that my W. So this is going to be X minus 3Z minus 4W equals 0. The next row is going to be, let me give myself a little bit more space here. So this is going to be Y equals 5. And then this last row is just going to be all zeros again, okay? But here's the catch, or here's the thing. You do not have a leading entry in that third column. So therefore, I'm sorry, I said third column. Let me repeat that. You don't have a leading entry in that third row, which means this Z and this W are going to be anything I want it to be. Now, in about a semester or two, some of you may be taking a class called linear algebra, and this is all it is. We call these two right here free variables. And what that means is they can be any value that we want them to be, okay? So what we're going to do here is this. We're going to say, let Z equal the letter S, and let W equal the letter T. All right. So instead of writing 0, 0 in this linear system, I'm just going to go ahead and just write, and let me put it in the proper column here. Z equals the letter S, which is going to be any number I want it to be, and W equals T. And I guess I'll just put S comma T are any real number, okay? So now if we were to write this in its proper form, and remember what I mean by proper form is x, comma y, comma z, comma w, we're going to have to solve all these for their respective variables. What's really nice is you already know that y is 5, z is the letter s, w is t. The question becomes, well, what is that x? So let me just write this real quick. We have x minus 3z minus 4w equals 0. Just make the substitutions. X minus 3s minus 4t equals 0. And then we're going to solve this for x. So x will equal 3s plus 4t. And that's exactly what you're going to put in this very first component of this point. And that's your answer right there. So in this situation, once again, this is 100% consistent, meaning, yeah, we got a solution. However, it's also dependent. And the reason for that is because you have free variables bouncing around. All right. Whew, this was a doozy. So like I said, and I think I posted this in the announcements, this section you will spend the most time with because it's just time consuming. A calculator really helps. However, you still have to know how to write your answers properly. So good luck, and I'll see all of you in the next video.